because time is short and I'm standing between you and lunch. So, great pleasure to be here. It's my first time ever at OPLSS and my first time ever in Eugene. I think the closest I've been before was Corvallis, which was fun. Great to be here. I'd like to get to know as many of you as possible while I'm here. So, please come up and talk to me. I'm very nice and easy to talk with. So come and tell me why you're interested in PL research and why you came to OPLSS. I wanted to start with this quote. So the book, gosh, it takes me back to my teenage years. The book came out in the 50s, and a little while after that, I got that book, which I loved. It seemed very subversive, how to lie with statistics. And it's a great book about how lots of people in power manipulate statistics by things like abusing what is on axes or missing out bits of axes. And there's various tricks that the book explains. So that got me very intrigued. And what this book is about, in a way, is like how to empower people with an understanding of statistics to not be fooled by those in power, whether it's people who are trying to sell you things or people are trying to govern you or whatever. And in a way, this is the long-term motivation for the kind of research that I want to tell you about. And there's also this great quote from H.G. Wells: "Statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write." I'm here to tell you that PL design, PL theory is a way where we can actually have an influence on that. So I hope I can get you excited about it. Here's my title: Empowering Spreadsheet Users with Probabilistic Programming. This is joint work with a great many colleagues. I guess I'm reporting a series of POPL papers and other bits of work that we've done. And we've done that with a range of collaborators at Microsoft, including interns. And I'm very keen to have interns come work with us in our group in Cambridge. So do talk to me about that. That's my Twitter handle, Andrew D. Gordon. Our group webpage is aka.ms Calc Intel for Calc Intelligence. We're trying to bring intelligence to spreadsheets and end-user programming. And we do a lot more than I'm going to be able to talk to you about today. And also this page here is aka.ms POPL is a page we put up for this year's POPL to tell people in the PL community about some of the work that goes on in PL at Microsoft Research, all up at our labs in Redmond, in Bangalore, in Cambridge, and elsewhere. Okay, so let me start with a definition. What is probabilistic programming? The basic idea is you start with your favorite programming paradigm, whether it be functional, logic, or imperative. You have some kind of way to introduce uncertainty, probabilistic behavior, usually called random or sometimes called sample. And you add constraints to condition on the observed data, and you indicate which variables distributions are to be inferred. That sounds a bit abstract at the moment. I'm going to give you lots and lots of examples over the course of the next few days. Why do this? It's better. The basic reason is that we want to get compilers to do some of the hard work. It's really hard to build a statistical model and figure out how to do efficient inference on it. And some machine learning models are also statistical models, and the same goes for building machine learning systems. So the idea of probabilistic programming is that we have a compiler will do a lot of the hard work of doing efficient inference, and the person who writes the model just describes their intent and then leaves much of the hard work to the compiler. That's the goal, the aspiration. There's a great many systems, and I'm not going to read them all out, but I just want to give you credit that there's a great many different research systems that have been invented. I'm about to tell you about the big four that kicked off much of the work. And there's been academic prizes come from probabilistic programming systems. At Microsoft, probabilistic programming around the infer.net system and also Tabular that I'm going to tell you about have been used in some large-scale services, such as something called Microsoft Office Clutter, which can reorganize your inbox, and also Trueskill, which is now widely used in many games on Xbox. In terms of the formal programming language semantics, the pioneer probably is Dexter Cozen, who started writing papers about probabilistic programming languages back in about 1980, he wasn't really at that point thinking in terms of doing statistics or machine learning. It was more like, if you had a probabilistic programming language, what would it actually mean? How could you sort of figure out the challenges of combining potential non-termination with also probabilistic behavior? And then there was Giry introduced the Giry monad for thinking about the categorical semantics of probabilistic programming language. In '89, there's a very influential paper by Claire Jones and Gordon Plotkin that introduced an operational semantics for probabilistic programming languages and related it to a denotational semantics. Prakash Panangadan has written some great expository texts about semantics of probabilistic programming languages, and Ramsey and Pfeffer did some very nice work at POPL some years ago. And in fact, this is all kind of before about 2010. There's been a lot of work since then as well, but this is really the pioneers. I just want to give some credit. Okay, so big four probabilistic programming languages. First one is called BUGS, which stands for Bayesian Inference Using Gibbs Sampling. And incredibly, it actually started in '89 in Cambridge. And I actually was doing my PhD in Cambridge at the same time. But I had no idea that in the stats lab, these guys were introducing this funky new way of thinking about programming languages. So BUGS was really the pioneer, and there wasn't any other work for decades after that. And they started out in the stats community and figured out how to write statistical models in a declarative way, and then they used this inference mechanism called Gibbs sampling to do inference. Infer.net started at Microsoft Research 15 years ago, 15 years after BUGS started, actually. And it was largely inspired, syntactically anyway, by BUGS, but they used rather different inference mechanisms based around what's called message passing. And I'm going to go through some of their slides shortly to show you roughly, just to give you some sort of intuition for, in fact, both message passing and sampling methods. And then Church, about maybe 10 or 12 years ago, 2007, 2008, Church, a language for generative models. So the big innovation here was that they started from a Turing-complete programming language. The languages that these systems were talking about were not Turing-complete. They had iteration over the size of a data set, but they didn't have unbounded loops. The guys from MIT, Goodman, Mansinka, Roy, Bonowitz, and Tenenbaum, they basically took a dialectic scheme and added the ability to do random draws from it, and then invented a new kind of sampling-based inference. And it means you could write almost any machine learning model, or at least probabilistic machine learning model, using this scheme dialect that was called Church. And they were able to do inference, not always efficiently. There was a bit of a trade-off. The more general you are with the modeling, it means that your very general inference mechanism perhaps won't be efficient in every case. So I guess they introduced a big research area of how to do more efficient inference in these very general purpose. They're called universal probabilistic programming languages. And then the fourth one I want to call out is Stan. Now, Stan, in a way, started out as a dialect of BUGS. This again comes from the statistics community, this time around Columbia University and Andrew Gelman, who is possibly the world's greatest living Bayesian statistician. He's certainly written some great books and is very well known. And a team around him, and also Bob Carpenter and others, started building this new, basically a reincarnation of BUGS, but using a different inference algorithm. And they've built a really big open source community around Stan, and a huge manual, 600 pages. So it's a very exciting probabilistic programming language. But like these two, it is also, it gets a little controversial. Is it universal or not? Maybe I don't want to get into all the arguments about that just right now. I would say it's closer to these, and it's not as general purpose as something like Church, but that's a bit of a contentious point. So, what is the plan for these 3 lectures? Today, I want to introduce you to probabilistic programming in Infer.net. So I'll go through some specific examples, and then talk about Tabular, which is a system that we have built that is aimed at taking the power of probabilistic programming and putting it in the hands of spreadsheet users. So I'm going to go through a bunch of examples and trying to give you a sense of what probabilistic models look like. I'm not going to go into a huge amount of rigor about the semantics, but instead I want to give you a sense of what these models look like. Tomorrow I'm going to talk about, I'll probably continue to finish off talking about Tabular and then get on to Fabular, which is an enhancement of Tabular with something called formulas, strangely enough. And then I'll also talk a bit about Stan and some work we've done recently on the semantics of Stan. And then finally on Wednesday, I'm going to look specifically at end users and really start from the end users and say, well, in a way, this big project is to try to take statistical modeling to end users. And I have to admit, for many years when I was doing this, I didn't speak to a lot of actual end users and ask them, what do you want? You know, what are your problems? And so I've come to realize that in some sense, programming languages is a subset of HCI. You know, when we are designing programming languages, and even when we're trying to understand the semantics, it's about HCI. And if you're doing HCI, it's important to talk to users, actual people, to see what it is they're trying to do and how you can solve those problems. And so on Wednesday, I'll talk about some interview studies we did with Spreadsheet users to figure out, well, actually, what were the problems they were having with understanding data and uncertainty in data, and where are the places that probabilistic programming or variations of it could make a difference. So overall purpose, why are we doing this? Well, I started with a quote from H.G. Wells. I mean, that's what, in a way, that's what's driving me, is to take insights from computer algorithms and designer programming languages, put them in the hands of end users to try and allow anyone really to have a better grasp of statistics. Who are we doing it for? Well, really for anyone, a really large population of people. So we need to start thinking about different kinds of people and who actually we can make a difference for. More specifically, I'm going to try and give intuitions of how we are doing this. So I'm going to try to give you a sense of what it's like to program in these languages. And finally, some challenges for the future, because you folks in the room, you've worked pretty hard to sit on those desks. You know, you've learnt a lot. You've worked pretty hard. And I can tell you're all eager to make a difference in your PhDs. So I want to, like all the other lecturers, want to give you some challenges for the future. Okay, so let's get cracking. A simple example, and I've stolen most of these slides from Tom Minka, who's one of the originators of Infer.net. So, very simple example. I secretly toss two coins. I tell you that they're not both heads. So what's the probability that the first coin is heads? In fact, you could probably figure that out. They're not both heads. That sounds about right. So I'm having a mental blank just right now. Let's say that's right. There's 4 possibilities, and we've dropped it. It's a third. The answer I want to say is a third. Okay, let's go through the details. I'm sorry. I'm feeling a little jet lagged just right now. But let's go through the details. So how do we specify? Seriously, how do we specify the model? So there are. Let's see. So we could we could write out the probability distribution from first principles, like just from the mathematics of probabilities. You could write something called a factor graph that I'll explain in a moment. Well, I'll show you what they look like. Or you could build a simulator, which basically is a bit of code that sort of runs the experiment. You know, tosses a couple of coins and also asserts that not both are heads. So let's look at those different possibilities. So a model for a fair coin. So here's the probability distribution of a coin. So a coin could be either 1 or 0, and the probability of either is going to be a half. Because if you take 1 minus 1, you get 0. Anything about 0 is 1. You could write a factor graph. So a factor graph is a way of sort of breaking down a probability distribution into writing a joint distribution over a number of variables. And we've got 2 kinds of nodes in the factor graph. There's a circle nodes are the actual random variables, which is the coin, one coin in this case, that can be either 0 or 1. And these square nodes are constraints that you place on the random variables. And in this case, we're saying we're going to place a constraint on this, that its prior distribution is that it's a Bernoulli, say Bernoulli a half. So that's just simply notation at this point. Or you can write a simulator, which would literally, call the random function, and then return true if it's so random's returning, doing a draw between, uniformly between 0 and 1. And if we ask it whether it's less than a half, then that'll give you a fair coin. Okay? Those are the three possibilities. And then for the two coins problem, you could write this directly as probabilities like this. You multiply together so again, this is a joint distribution over two variables, coin 1 and coin 2. And so the probability of any assignment, there's 4 possible assignments for coin 1 and coin 2, is like the product of their priors together with this constraint that will go to 0 if both in fact are true. As a factor graph, you can write it like this, where we've got the three constraints. Sorry, the three random variables, and then these are the constraints on them. Or you can write them as a bit of code like this. So this is simple probabilistic programming. And in a way, part of the point of all this is that this is a lot easier to think about, as programmers, that we toss a couple of coins and then we set a flag to say whether or not both are in fact true. And then how do we do inference on this? There are different approaches. Basically, depending on which of the different formalisms that we're dealing with. So you can do integrals, you can do simulation, which I'm about to show you, or you can do message passing. And let's look at simulation, which is very simple to think about. And this is the point where I should be able to remember what's going on. So here we do one run. So we flip coin 1, and it comes up true. Flip coin 2, it comes up false. And so both heads is false. And then we do another run. So false, true, false. Another run, true, true. And this time this is going to be true. And then true, false, and then false. So that's 4 that we've done. And then we repeat. And the way of doing simulation is you run a lot of these. And then you want to place a constraint. You actually want to condition the model. So far, remember I said that in a probabilistic programming language, we've got, 2 main ingredients you've got the ability to introduce randomness, which you're seeing here, but you also have the ability to actually apply a constraint or to do conditioning. And that's so you would do that first of all, sorry. After many runs, you get down to this, that you got 50-50 for these coins, and then 25% of the time, this comes up true. And then if we observe that both coins is false, then we're basically chopping out a whole lot of the runs where both heads is false. And in that case, we get back to the probabilities that we were saying, that coin 1 ends up being true a third of the time, same for coin 2, and both heads is true as 0% of the time. Okay? Message passing is an alternative, and so the problem with doing the simulation is that it's very expensive, and in fact you waste a lot of work to meet the condition. So message passing is a much more efficient alternative, and I'm just going to show you the gist of how message passing works. And you'll see that it takes far few operations to do the computation. Okay, so we come in and we've got this factor graph. So this is coin 1 and coin 2, and then this is the flag that is saying that both in fact are true, and we've shaded it in to indicate that we've constrained it not to be true. Okay. So the way message passing works is that we want eventually to get distributions on each of the random variables, but these factors place constraints on the random variables. So initially, and the way the constraints are solved is by sort of local message passing on the graph. So in this case, the two Bernoulli factors constrain coin 1 and coin 2 to be a fair coin initially, and then they pass that information down to the AND, and then what it does is send back the information that because not both are allowed to be true, we send back this message here, which is going to constrain the coin 1 based on the information from the rest of the graph, which is the coin 2 and also this both heads is false constraint. So the messages are structured based on a probability or a weight, if you like, for true and false. And so the message coming back basically places no constraint on false, because whether or not it's false won't affect whether both coins could be true. But if the coin 1 is true, then the rest of the network, and in particular the fact that there's a 50% chance that coin 2 might be true, causes us to push a message back that constrains the true, whether coin 1 is true by 50%. And the same is true for coin 2. And then these are multiplied together, and so we end up with these distributions on the two coins. Now these, we have lost some weight. We sort of chopped out a quarter of the probability by ruling out the two coins as true, and so we need to renormalize. And so we do that and end up with this distribution here, which is the same as we got from the very slow rejection sampling. So that's just giving you an intuition of how message passing works. I'm not going to go into all the details of it. You can go look at Tom's paper. But the thing to take away from this is it's very fast. It just, the messages come down and come back up. And also in this case, it's exact. Now, unfortunately, it's not always exact. And what in general Infer.net has to do is to iterate, where you have a number of you maybe have a big graph of random variables, you pass messages around, and you have some number of iterations hoping to hit a fixed point. And sometimes you don't bother, you just keep going for a while, and you get a reasonably sort of good enough answer. A thing that startled me when I first started working in machine learning was to realize that unlike PL, they don't obsess about absolute correctness. I mean, after all, it's a bit of a messy, data-driven exercise altogether. So often, if you've got enough data or a good enough model, getting an approximate answer to your problem is much better. Getting an approximate answer quite fast is much better than getting an absolutely correct answer. Okay, so the point here, I kind of said this already, but we want to build a compiler. The overall goal of Infer.net was to build a compiler that, given models for machine learning situations written in code, but of the style I've shown you, where we don't code up what the inference algorithm is, you simply code up the model, it would turn that into efficient inference code. And so they built Infer.net starting in 2004. And here is the structure of it. It's a compiler. You take a model in as a bit of code. There's a number of transformations on the bit of code that eventually leads to a factor graph. And then we have an inference compiler that turns the factor graph basically into code that executes the message passing that I showed you. And then it gets executed given actual data, and it produces results. So fairly straightforward flow diagram for a compiler. But I really want to emphasize it's a compiler. And so here is the actual code you would write in Infer.net, where you'd say coin 1 and coin 2, and you would use this. They've got a class of random variables, and so coin 1 and coin 2 are both declared as random variables that are fair coins, and then they compute both heads by conjoining together coin 1 and coin 2. They build an inference engine with their object model. So this is the actual code you'd run. And then given this Bernoulli model, given the model that's been built up sort of in imperative state, they can then infer what Bernoulli is, what both heads is. And in this case, they're having to actually pass in the fact that it is a Bernoulli distribution, and you get this answer. And that's before, right? So that's beforehand, before applying the constraint that the two coins must be true. And the way that can be done is by saying both heads to observed value is false, and then they do inference again, and you get out this distribution. Okay. I'm just pausing. I'm supposed to leave you a 5-minute break at some point. Let me see. I think this. Maybe I'll speak about this, and then we can take a break, and I'll get on and talk about Tabular. Okay? So, I feel like going a bit longer. What do you think? Do you feel ready for a break at this point?
Let's just keep going.
Okay. Sure.
In the previous example with just like pseudocode, the fact that coin 1 and coin 2 were both binomial was expressed in like the type as a bool, whereas here it's just like a variable, and then presumably the fact that you got Bernoulli shows that it's like a binomial variable, right?
Bernoulli, but yes. Yep.
Sorry, Bernoulli.
Yeah.
If you wanted to generalize that to just like say like a multinomial variable or something like that, would you be able to reflect that like in the type system as well?
Yes. They have. I mean, yes. There's a separate class of well, first of discrete distributions. I mean, so a Bernoulli is like a sort of a discrete distribution over two values, and then they've also got a discrete distribution over like many values, or a fixed number of values. So yeah, there's generalizations.
And then in the conceptual version with like the pseudocode, would that just generalize with sums rather than just the bool?
Sorry, say that again.
Would that same idea generalize in the pseudocode version using sums rather than just like a bool as the type of that variable?
Yes, you could do computation on the. Yes, you could do something like sums on the numbers obtained from a discrete distribution. So yes. All right. So empowering spreadsheet users. So starting to think about people. So Pat Hanrahan is a very famous graphics researcher at Stanford University. In fact, he actually. Is named as one. He's given credit from Toy Story 1 back from 1995. So great in graphics, but then he got interested in data as well, and he did research that eventually led to with others to the founding of Tableau, which is like a big company in business intelligence that in fact recently was in the news. But anyway, so he identified this class of people called data enthusiasts. So you've heard about professional programmers, you know about data scientists. And so these are both people who have like professional expertise in programming, and they know a bit about, say, stats and ML, or a data scientist, someone who's got professional expertise in statistics, and maybe knows a bit of coding, but mainly they're really expert on statistics, maybe know how to code in R and so forth. Pat identified this much larger class of people who do not see themselves as professional programmers or statisticians, but they know a bit. It's more like they are professional business people, like maybe they're a surgeon who is interested in why it is that wants to look at what happens, why it is that some patients are returning to hospital, do an analysis of that, or maybe it's a car salesperson who wants to figure out why it is that sometimes people buy the cars and they don't. So they're really like a business person who wants to get some, get value from data. So this is I think the data enthusiast is a sort of modern day 21st articulation of what H.G. Wells was talking about. The kind of people who would want to sort of use data to understand business and society. So data enthusiasts are the people I think ultimately we're trying to reach. In my own work, I don't think I'm there yet, but I'm putting this up as an aspiration of where we're trying to go. So that's what we did with Tabular, that we wanted to come up with this. We looked at infer.net. We thought it was pretty cool. We looked at the spreadsheet and thought, there's a lot of people have got, maintain data in the spreadsheet. Wouldn't it be cool if we could take infer.net and put it in the spreadsheet? And in so doing, we thought, well, we can't really expect the data enthusiast to write C# because they don't see themselves as a programmer. Instead, could we come up with some sort of DSL that would make it easier for them to write queries about their data, apply machine learning to their data? So we had 3 guiding principles. Key idea was that the data enthusiast is already comfortable. So this is an assumption, but anyway, the data enthusiast is comfortable with the idea that their data is already organized into tables. And modern spreadsheets basically have merged in database functionality. So Microsoft Excel has got an in-memory relational database, and it's got a UI for building relational schemas. And so we thought, okay, if the data enthusiasts are already comfortable with that, what if we could hang the probabilistic programming model off the structure they already have? So that was the starting point. Then inference. So inference would be by querying. Well, I'm saying it. I'll explain this by example, what I mean by that, querying latent variables and missing values. And a third principle that is still a challenge. So if you want a challenge, this is a good one. How can we auto-suggest models based on the structure of the data? So we think we've got some great languages here for defining probabilistic models, but we still need to do some work on discovering new ones. Okay, so let me say a bit about the structure of a model in general. So this is a very simple example, but it can be generalized a lot. But let's just stick with this very simple example. So this is linear regression. So the problem will be like this. You've got your blue data. You've got these data points, and you're trying to fit the best, trying to figure out the straight line that goes through it. Now, there's actually some classic algorithms, from centuries ago for how to do this by sort of minimizing the square of the what's called the residuals, which is the gap between each point and the line. But let's suppose we didn't have that. How would you do that in a Bayesian style? Well, the idea is you want to have a model like this that says that each y is a function of x. So it's ax plus b. So a is the slope of the line, and b is the intercept. So b is the point when x is 0 that the line goes through, like say 10 in this case. And there's always an e, which is a sort of error or a residual, which is the gap between the prediction and the actual value. And in the Bayesian approach, we put distributions, probability distributions, over the parameters. And in this case, we're going to say each error is drawn from this distribution. So what is this notation? N0 2 squared. How many people recognize that notation? Okay, at least half of you. Good. So this is the normal distribution, also known as the Gaussian distribution. And there's two numbers. The first one is the mean, which is the point in the middle of the bell curve. And the second one is the variance, and it's the square of or sigma squared is usually how it's said. And so sigma is the standard deviation, and which is like this gap here. That's sigma to the left and right of the mean. And this the distribution is usually given in terms of the variance, which is the square of it. Okay, so that's that distribution. And the parameters in this case, we're also going to give these distributions. You might say, why these distributions, Andy? And I'd be saying, yeah, you're right. And you're asking me why these particular priors. And the Bayesian would say, well, this is your best view before you see any data for what you think those numbers are going to be. And you hope that as you get more data, you learn more about these distributions, and it's sort of eventually, your initial assumptions eventually are removed. There's a lot to be said about priors. But anyway, I'm going to pick those particular priors for the sake of discussion. Now finally, here's a bit of tabular. So if I was to, so yes, what do we have here? This is the schema for a table with some probabilistic annotations on it. So the data that we're modeling are x and y. So xy is the name of the table. X has type real is one column, and y of type real is another column. And so if this was just a database schema, you would just see this part here, okay? But in addition, I'm adding information about the model. So in gray, I've got these static latent variables. And so static means that although they're in this database schema, there's only one occurrence of them. We're calling it static by analogy with objects. So an object in a static class, there's only one of them, whereas anything that's not labeled static is sort of per row in the table. Okay, so there's only one A and one B, but there's many X and Y, one for each row in the table. And latent means that it's not directly observed, so it's not actually present in the physical data that you're given, but it's part of the way we model the situation. And then on the right here, in this column here, we put any probabilistic models we have. So for our latent variables, we give them these Gaussian distributions. Oh, and there's a typo. That should be 2. Sorry, that should be 4. No, I'm wrong. So those correspond to to that distribution over there. And down here we write the model, and we just say that the y we think is distributed according to a times x plus b with the with this variance here. Okay, and so in the jargon, these are known as parameter distributions and often written like that. And this is often known as the sampling distribution. So it's written like this. So in this probabilistic notation, think about these guys to the right of the bar as being sort of inputs to a function. So it's saying, given a, b, and a list of x's, what these two lines are defining is how you produce a vector of y's. And it's saying you produce it by, for each x, calculating this formula here. And then the predictive distribution, which is the formal model that we've defined of our data, is this guy here. It's saying it's the distribution over the y's given the x's. And pictorially, we're showing that up there. And in using the sort of integral notation, it looks like that. It's saying well, say for any choice of a and b, the probability of y vec given x vec is the product of PAB, the parameter distribution or the prior distribution, with the sampling distribution for any particular choice of a and b. And then what the integral is saying, well, all right, we don't know what a and b are, let's just sum over all of them. And so that's the effect of, I mean, obviously an integral is like a sort of sum, a sort of infinite sum of, infinitesimally smaller and smaller sort of strips from the domain of the function. But we just think about that intuitively as being a sum. And then when we've got no observed outputs, these are known as prior distributions. And any time we condition on actual observed data, we get the posterior distributions. So, these are just the priors over A and B, but then once we actually have actual data, these will be updated by parameter inference, and that will be the posteriors. Okay, I think I will do my 5-minute break right now. There's a question before we break. The noise is being given, great question. Maybe we're a bit fat. The noise has been given here. What we've done is we've taken ax plus b, and then we've said that's the mean of a Gaussian, and it has the with 4 as its variance. See? Okay. Any other questions? Okay. Let's take a very quick break, just 5 minutes. So it's now 20 past. So I'll resume at 25 past. To give credit, so the picture of Judea Pearl, Turing Award winner who invented message passing, and Stanislav Ulam, who first invented Monte Carlo sampling a long time ago, 50, 60 years ago. And really just to call out the differences that with sampling-based approaches, you have a set of samples to represent the joint distribution. It's slow, but it can be very accurate. And something like Stan is a very nice example of a probabilistic programming language. Really, in fact, guess why it was called Stan. And message passing, we don't directly represent the joint distribution over a whole lot of variables. Instead, what you do is represent the marginal distribution. So you just look at an individual variable on its own and saying, well, what is given by summing out all the other variables? What is its distribution? So this is, and it's very so it's approximate just by construction because it doesn't directly represent the joint distribution. And then the algorithms it used are also approximate, but they can be very fast and in many cases can be useful. Okay, I just wanted to say a bit about factographs in the context of the example, my very simple linear regression model. And I wanted to introduce something called plate notation that I'm illustrating here. So this is the graph, and it's got 4 random variables. So it's got A and B, the parameters we're trying to learn, and then it's got the input x and the output y. But actually, it doesn't just have 4 variables, because these 2 are enclosed in this box that is known as a plate. And think about this as being an array operation. It's saying that there's an array of replicas of that bit of the graph. Okay? So in this case, think about it as there's 1 replica of this bit of graph for every row in the table. Okay? And the convention is you put the size, in the top left, you give a number. In this case, it's the size of the points array, which is the number of replicas of this guy. And then there are 3 factors, which is where factor graph comes from. That's why it's called a factor graph. And 2 of these factors are putting priors on our 2 random variables. And the other one is here. And this actually, in effect, connects the 2 parameters A and B, and also each input variable with the output variable. And this is where we actually have the generative model, where we say that the output Y is a Gaussian with mean AX plus B and variance 4. Okay, and then just in mathematics, this factor graph here is just a sort of visual way of representing this formula, which is saying that the joint distribution we're defining, so a joint distribution is over like a tuple of things, and it's saying what is the probability of a particular choice of those things. So in this case, it's the probability of a particular values of A and B, and a vector of X's and a vector of Y's, and it's this number. So it's the density of this Gaussian distribution at A, the density of that Gaussian distribution at B, and so that's a density. And so one of these is just the height at a particular value. If B is there, then that is the density. And then finally, you get the density of that Gaussian distribution at Y, and then we take the product of that for each value I in the array of points. Okay, so the factor graph is just defining this particular function, but it's a nice representation that where the graph is capturing locality, and that is exploited by these message passing algorithms. Okay, so back to tabular. So a recipe for doing probabilistic modeling is you start with a schema, you add latent columns, which will, a bit like the parameters you've seen so far. We write models for the latent and output columns, like the model we had for Y. We then do inference and we learn the latent columns and the table parameters, and then we can predict missing values in the output columns. And tabular focuses on this part of the cycle the data enthusiast would go through. The data enthusiast also needs to do stuff like importing data and cleaning the data, which is a very time-consuming thing and needs specialist tools, and we're not trying to address that. And we also need to do stuff like visualization of the outputs, and we've not really emphasized visualization, but those are important. Okay, so let's talk about Trueskill. So this is like a classic for infer.net. And was first deployed for Halo 3 back in, 2006 or sometime. But it's still going strong, and it's now a service that's provided to lots of games on the Xbox platform. So here, let's start with the schema. But there's the schema. So you've got some data. So what is this all about? We're trying to figure out how skillful people are based on the outcomes of matches that they've had, pairwise matches that they've had. And then if we know people's skills, then we can do matchmaking. So in an online game, you want to match together people who've got roughly similar skills so that everyone has a better experience and learns. So that's the task we're trying to perform. So here's some example data. We've got Alice, Bob, and Cynthia with their indexes. These are like primary keys. And then we've got a couple of matches where this is saying that Alice played Bob and player 1 lost. So it means that Alice lost to Bob. And this means that Bob played Cynthia, and again, player 1 lost. So Bob lost to Cynthia. So then this is the schema of the data. And now we've got 2 different tables, unlike the previous example. And we have these... We have an indication that some of the columns are in fact primary keys, foreign keys into other tables. So player 1 and player 2 are actually pointers or links or foreign keys to the players table. Okay, so then here's the actual model. And that's it as a factor graph. But let me just explain how it works. So the first part is that we add a latent column, skill, to the players table. And obviously this doesn't actually exist in our existing data. That's what we're trying to figure out. and we don't know what it is. So conventionally, we say that the skill is going to have a mean of 25 and a standard deviation of 10. So that means that I think about 95% of the time, that skill is, if it's drawn according to that distribution, it's going to fit between 0 and 100. So that's the prior on the skills, and then this is the program that predicts whether win1 will be true. And we have another couple of latent variables in the matches table. So the basic idea is that player 1 is going to win if player 1's skill is higher than player 2's. But that's a bit of a crude model because there's always elements of luck in any particular game. So it's not always, think of football. It's not always that the more skillful team wins. And also players have off days. So we add a bit of noise, which is a standard trick in probabilistic modeling. Don't make things too exact. Add a bit of wiggle room, so add a bit of noise. So that's what we do here, where we add a bit more Gaussian noise. So we say that the performance of 1 is player1.skill, so that just gets the skill of a particular player, and we add a bit of noise to it with the same standard deviation as for the skill. And then we compare the performances. Then as a factor graph, it looks like this, where we've got two tables. So this plate is over the number of players, and so we've got a skill for every player. And then this plate is over the number of matches, and so we've got skills. Sorry, these are inputs. So these are given to us, player 1 and player 2. We don't have any model for them. They're simply, the whole thing is conditioned on them, but we can't predict them. But we do have these latent variables, which are not observed, but they are sort of predicted by the skill of player 1 and player 2. And then finally, we do a comparison between the performances, and then that's our prediction of the winner. And so if we see that visually, it looks like this. I'm going to give you a demo shortly of a slightly different model, but this is what you would get if you run this in our system, that given this particular data set that I spoke about, remember we had that Cynthia beat Bob and Bob beat Alice. And so what happens is the latent columns get updated. So this is where you're seeing some Bayesian update, where, remember, the skills initially a priori were like a mean 25 with a big standard variance of 100, and you can see they've gone down. So Alice has dropped below 25, Cynthia's gone above 25, and we're a bit less uncertain. We've got more information, so the variance has shrunk. And then the performances, which were used in the predictions, these tables, they are like copies of the the noisy copies, in fact, of the performances of the skills of the players. And because you've added noise, they've got a much bigger variance. And the means have shifted around a bit as well. Okay, and then query by missing value. We actually want to make predictions out of this. So naturally, you want to predict who's going to win. So let's add another row to the plays table. And this time we're going to have Alice playing Cynthia. And it's going to predict, in this case, that it's not certain, but it's pretty unlikely that Alice is going to win against Cynthia, who will probably win herself. Okay, so that's a basic example. This is a more complicated one. This is one we built. This is American college football that I'm a bit ignorant about. NCAAF. Does that mean anything to anyone? Ah, okay, perfect, right. So this is real data from a little while back, or did you just make that up? Is that? I think that's right. No, it's right. Okay. Okay.
It's only be controversial with this.
Typically, people just use NCAA as a single opaque signifier, and then that stands for football.
Okay, yeah, that's roughly how I think about it. Pardon? Really? Okay. Thanks for the information. I'm kind of approaching this in a Bayesian way. I'm not sure. Yeah, right. Okay. So this is a bit more complicated, but it shows that how we basically you can kind of combine together these modeling tricks. And so here we have a bit of hierarchy. So each team, so roughly we're generalizing. Beforehand we had a player, now we've got a team. But the generalization is each team belongs to a league. And so the idea is that at the league level, we've got a table of leagues, and each of those has got a skill modifier. So I guess some leagues are better than others, and this model will try and learn that. And so when you have each team has got its own individual skill, and then overall its skill is given as the sum of its individual. The skill that we regard it as having is the sum of its sort of local computed skill, the overall one from the league. And this is known as hierarchical modeling. And then when we predict the matches, in this data set, we also have an indication of whether the team is playing at home or not, which we get from a Boolean somewhere. Team 1 was home, which is given as a 0. It's given as 0. It's a Boolean encoded as a real in this case. And so the home advantage is the product of team was home with the home skill advantage. And so that gets added in here when we look at the performance of team 1. But otherwise, it's very similar to the previous model. And we did a bit of an assessment of that by looking at a data set, and we had, so the x-axis here is where the team came in this collection of experts. There's ranking computed by experts, which is what we've got here. I think this is the Associated Press. And then what you're seeing is the predictions that we get from the model. And note they're uncertain. So what we're plotting here is, I think this is like 2 standard deviations away and the mean. So you can see roughly this is forming a straight line, which is what you would hope. Okay, so let me move on to a demo. And let me set it up a bit. This is like a research paper from the security community that did a bit of Bayesian reasoning, and they did it from scratch. But what I'm showing here is how we can build a probabilistic model in Tabular for this scenario. This is a paper called Lest We Remember Cold Boot Attacks on Encryption Keys. And the basic idea here is it's a bit of a slightly plausible scenario, but in computer security you want to look at all the sort of angles. So the idea here is someone's got a laptop and their DRAMs hold unencrypted data. In fact, this is in the days before people went to lengths to encrypt sensitive information when it was in main RAM. So supposing you've got clear text keys in main RAM, there's a potential attack would be that sort of gets around the operating system protections, is that you take the computer. Well, first of all, before I describe the attack, here is the problem. That this is showing this particular image in main memory and how long it takes to decay over several minutes. So if you can basically get at this DRAM within a few minutes, you can extract this encrypted information. This sensitive information. And the way they did it was that they took the machine while it was still on, and they sprayed it with this freezing stuff to take the DRAMs down to -50, and you see it's all frozen. It's now switched off. They take the thing out. This has taken 6 minutes, and then at this point they put this into another machine and extract the information. So here's the model. The idea is that you've got a whole bunch of, so there's some facts here about the DES keys. The way the algorithm works is that it sort of requires there to be multiple copies in memory of the same key bits. And we're going to exploit that in the model. So the idea is that every bit, in the model, every bit is going to be copied 4 times. And then the way in which the bits decay is actually asymmetric. So the probability of a 1 flipping to 1 will sort of model as one particular decay rate or probability, and the probability of going the other direction is a different decay rate. And we have a probabilistic model that can track both of these. And before I get into that, let me just explain the distributions we're dealing with. So we've talked about the Bernoulli distribution. We've talked about many times. It's just like the bias of a coin. But if you're doing hierarchical Bayesian modeling, where you have like a distribution over another, you've got a parameter that defines properties of the distribution of another parameter. We need to have what is the distribution over the biases of coins? Well, this is known as the beta distribution. So this is a distribution, it's a continuous distribution over a bias, which you can see here, which is the unit interval here. And intuitively, beta alpha, with the parameters alpha beta, is the distribution over the bias after observing true alpha minus 1 times and false beta minus 1 times. So in particular, beta 1, 1 is the distribution over the bias when you've seen nothing. So in that case, it turns out beta 1, 1 is in fact the uniform distribution. Okay? But then this plot here that we got from Wikipedia shows different values of beta. I'm not going to go into the actual formula for it, but you can see it intuitively here. So the purple one here that's alpha equals 2 and beta equals 5. So purple is the distribution when you've seen true once and false 4 times. So you can see it shifted so that if you knew nothing, the line would be flat. After you've seen false 4 times and true only once, it sort of shifts to the left so that we think the bias is around about here. And similarly for the others. So we're going to use a beta distribution as the distribution or as the prior for the bias of a coin. So right, let's go to Tabular. Okay, so all right, so I open up Excel. Great. And we have so what I did was I've already done this sort of beforehand. I chose particular values of decay 1 and decay, or 0, 1 and decay 1, 1. And then each row here has got the true bit, and then we've got the 4 copies of it. And so in this case, true, in the 4 copies, it's decayed twice. And in this case, it's decayed once. Can you see that? I'm seeing nodding. Okay, good. And in this case, it starts out true, and 3 times it decays, and once it doesn't. Okay, and there must be a false. And here's a false, and it's just stayed false. Which is in fact what you'd think, because the decay 0, 1 are set to be pretty low. So it's saying it's very unlikely for the zeros to flip to ones, but it's quite likely, sort of 50-50 more or less, that a 1 might flip to a 1. Okay, so that's some raw data that I've generated.
Did you generate the numbers, or did you hard-code it? How is the numbers in the column H and I their own thing?
These are all hard-coded.
Okay.
I think yes, I built, these are, this is just raw data. I think I built a wee model in Excel, but I've thrown that away now. But this is the data I used to generate it. And then over here, this is the data that I'm going to give to Tabular. Okay, so it's basically the same data, except I'm holding out these 4 bits at the end, which go false, true, false, true. Okay, so then I build a model in Tabular, and so that's it here. Let me make it a wee bit bigger. So here I've declared decay 0, 1 and declare 1, 1 as parameters. And I've given them beta distributions. So beta 1, 1 distribution. So it's basically just saying it's a uniform distribution over those 2 parameters. And then here's the actual model. So for the bit itself, so each bit in the row I know nothing about. I mean, it's just given to me. So I'm going to give it initially a Bernoulli 50% distribution. But I do know stuff about the copies, that they're all copies of the bit, but they're given by this expression. So it says, maybe it's easier if I make this bigger. Oh. That's, yeah, I've gone too far. Yikes. Oh, yeah. Ah, that's better. Right. Great. So you can see that each copy is saying, if the bit is true, then we flip the decay 1-1 coin, and if it's false, we flip the Bernoulli decay 0-1 coin. Okay? So that's the model. How do we run tabular? Right, so it's not loaded into Excel, so I have it here. And so we just drop it into Excel, enable it, and we need to switch it on, go to tabular, model, and it goes over here, and we have a bit of a UI, and if I just zoom out.
What did you click and drag?
So Tabular is a particular binary file, and I load it into Excel by dragging it into Excel. So that loads it, and then it opens up this. What's so funny? It's just this how you get an added going in Excel, and then and here I switched it on, and then it's come up as this sidebar. It's very cool, yeah. And there's I can. If folks are interested, I can go in a lot more detail one-on-one or later, but I just want to show you this quickly. And so I think I've not said, well, I'm not going to show you the UI, but the way I've set this up is that table 1 is the name of this table over here. So that's how the two link together. So each of the tables that Excel knows about have got names. This is the in-memory relational database that I mentioned earlier. And so in this tabular program, I just use the same namespace of table names that Excel already has. So that's how this gets attached. I don't need to tell the tabular add-in. It can read this thing and say, okay, that's a model for the data in the other table. And then if I just, again, I want, that works perfect. Right. So then hopefully if I say infer, then it thinks and it generates this model behind the scenes and then runs it. And then, this is perfect. That's what I should have done earlier. Right, so this is the results from Tabular. And what it's done is, it's for the two static variables, the one-off variables, they're listed here, decay 0,1 and decay 1,1. And remember, they started out as beta 1,1, mean a half. And the first one, it's figured out, basically, it's looked at the whole situation using message passing, and it's figured out that in effect, the decay 0,1 hasn't happened very much. So it's this beta distribution where it's seen it not happening about 10 times and happening about half a time. So its mean is very low. Okay, that's how you can read that distribution. And decay 1,1 is more likely, and so it's seen it happening about 30 times and not happening about 20 times, and so you get this distribution around about half. And remember, the actual value was, in fact, I think that was pretty much the exact value. And then if you look over here, this is the data. So most of this is input and given to it. So when it's an output column, and you actually have the data present, it's being constrained. So what Tabular does is just copy it over. So it's all the things before that were bits are now either Bernoulli 0 or Bernoulli 1. So they're either certainly false or certainly 1. But for the 4 that I didn't give it, it's figured out what the distribution is. This is the query by missing value part, and you see that it's not sure, but remember this was like false, true, and you can see that it thinks the first one is unlikely to be true. The first one is just over half. The fourth one is much closer to 1, and the other false is down there. So that's a wee example. I can show you much more later offline, but I've got 10 minutes and then it's lunch, so let me press on. Back to, let's see, in 10 minutes. Let me just continue about tricks and sort of programming idioms. So you're starting to see how people build up these probabilistic models with parameters that govern the parameters of other parameters, which is hierarchy. So let me show another example I think is kind of cool, which is called the use of this Bayesian reasoning to reason about performances and scores in tests. So this is like basically an intelligence test. In fact, someone, was it Henry, was asking me at break about, roughly, when is Bayesian reasoning appropriate and when is deep learning appropriate? The very quick answer is that if you've got a lot of data, like zillions of images, then deep learning is super useful. If you've got relatively small amounts of data, like this sort of scale, then handcrafting a model in this Bayesian style is going to work much better than trying to apply deep learning because there's not enough data. That's a very quick, rough and ready answer. Okay, so here's a bit of data where you've got a table of participants. So this is actually a screenshot of the data model that's built into Excel. And they've got a table of responses and a table of questions. And each question has got a true answer, and each response is the name of the participant, the question they were answering, and their actual answer. Okay, so that's the setup. And so what we want to do is have a model that can predict how skillful the participants are, how difficult the questions are, and even what the right answers are given the other participants. So let me show you the model. So this is the simplest model called ability, where we add an ability or a skill to each participant. So again, it's the same kind of paradigm. And again, we give it a Gaussian distribution. And precision is just the inverse of the variance. In this case, it's the same as the variance because it's 1. And each question has a true answer. And in this case, we'll just give it this prior distribution, that basically discrete. So I think it was Sarah was asking about generalizations of the Bernoulli distribution. So this is an example, discrete uniform, which is a generalization of that. And we give it this type. So I'm directly answering your question. So we have this up to 8 type, which is nothing to 7, which is a generalization of Booleans in the type system. And then for responses, we have the participant ID, the question ID, and then we have a wee bit of a model here that tries to predict what the answer is. And the rough intuition is that we have a skill, and if we're skillful enough, we're going to know the right answer. And so what it does is it sort of does this probabilistically. It says, well, okay, let's get a coin that's going to be whose chance of succeeding will be based on the person's skill. Let's flip it, and if it comes up heads, then we know the right answer because we can just look it up. That's what the answer is going to be. And if we get it wrong, then we just throw a coin for the answer. So that's what we write here. So we have an advantage. So we're making a copy of the... and this is one place where the beautiful abstraction has a leak, I'm afraid, where damp backward is basically a directive to the message passing algorithm to affect how it operates. So this is a guilty secret of some of these models, that they're not quite as declarative as you might hope. And there's points where you have to kind of give the inference algorithm a bit of a hint. So that's an example of it. But I want to be honest that sometimes, in fact, things aren't as pretty as I'm telling you, and you have to sort of understand a bit of how the model works. So we make a copy of the skill, and then probability advantage. So a skill, in this case, is actually any number. It's Gaussian distributed, so it could be minus infinity, plus infinity, it could be anything. It's pretty likely to be near the mean, but it could be anything. And so probit is a way, which is this function here, is basically a way of squishing an arbitrary real number down to a probability, i.e. a number between nothing and 1. And it's done basically by drawing a Gaussian based on the two arguments and asking if the answer from that is above 0. So that's the way it works. You squish this huge range down to a probability. And so that's the Boolean. We sort of flip that coin, so this is most likely to come out true if the skill is high. And then we say, well, if we actually know it, then we give the right answer. Otherwise, we give this guess. So it's sort of, I'm putting various concepts together, but we get this model. And it fits reasonably well. So log evidence. Well, evidence is a measure of how well a probabilistic model fits the data. And you want it to be, and the log of it, you want to have to be as positive as, we basically want to be as high as possible. So in this case, we're quite low, like minus 7,500, which isn't great. And that's because, partly that's why we haven't taken into account that some questions are harder than others. So let's add that. So we can add a difficulty to each question, which is another latent random variable. And now, surprise, surprise, we're going to ask, well, what the advantage now is the difference between the participant's ability and the difficulty of the question. So again, we're taking the trick beforehand in Trueskill, we were comparing two of the same sort, two players and their skills to see who was going to win. In this case, we're taking the difficulty of the question and comparing it to the ability of the answerer, and using that difference as a way to predict who's going to win. So then we take the difference, which will give a number, we squish that into a Boolean, and then we do the same thing as before. And now the log evidence for this has bumped up. Before it was minus 7,500, now it's bumped up to minus 6,000. And basically, what we did was we replicated a case study that had been done in fur.net, and it was rather large amounts of code, and we squished it down to this model in Tabular, which I think really captures the intuition of what is going on. And we did some, I don't want to go through these numbers, but basically they're showing that we got the same statistical results as before, much less code, and only a slight loss in performance. So we were pretty happy. I think we're coming up to 12. So as I suspected, I will need to leave some of the material about Tabular till tomorrow, so that's fine. But I've got a minute. I won't try and summarize the last 80 minutes. But does anyone have any questions at this point? Nima.
So because the interactivity in a spreadsheet is a concern, I was wondering if the algorithms like message passing that you described would offer that interactive rate. That is, so for example, one case in Excel's solver is that it's sort of like a VLOOKUP one-time thing. So if you do a change in your original data, it doesn't pick things up.
Right.
That's maybe partially because there's Excel uses like IOP, and it might be inefficient to run it like 30 times a second or something. So I was wondering if message passing is the same thing.
Let me try and summarize the question, because maybe not everyone heard it. So I think what Nima is asking is that generally in spreadsheets are highly interactive. You change some numbers, and any formulas depending on them instantly recalculate. And Nima is pointing out that the way we're doing this add-in in Excel, I had to press this button that was kind of completely disconnected from ordinary recalc. He's pointing out that some of the other tools, like there's something called Solver that can solve constraints, that again you have to press a button, and it's sort of separate from recalc. And I think the answer is yes, that's a good observation. I think generally in Excel, if recalc can happen almost instantly, or if your computation that you're adding to the spreadsheet can be implemented almost at once, then it's great to have that as a formula and now participate in recalc. In this case, the message passing is a bit slower. It's more like an analysis the data enthusiast would do. So we think it's probably inappropriate to do it as a formula. Or maybe that's too strong, but maybe that's debatable. But anyway, that's the way we've done it. So it's something to note, just in terms of interaction. We're not deeply part of the spreadsheet in the way Tabular has been set up. It's not using in fact, maybe that's another way of putting it. We're not directly using the formulas of the spreadsheet to define the model. Instead, we've got this new language that's written as text strings that Tabular understands.
But is there room for maybe make those message passing algorithms incremental or like self-adjusting or something so that you wouldn't need?
Great question. That's a great question. I don't know if anyone has done that, but that would be interesting to look at. Yeah. Yeah.
Does Tabular integrate with the online Nebraska basis?
Oh, it's a great question. No, it doesn't. However, it was built using an old technology that is specific to Windows, but there's a new add-in technology that's based on TypeScript or JavaScript, and so you can write an add-in that will run everywhere. And so so if we were to do it today, we would probably do it in TypeScript, and then it would run everywhere. Yeah, I'm a big fan of Excel Online. Yes?
In the case of something like the damp backward that you showed,
Yeah.
model, how would you as a user know to make that change?
That-
I think the initial observation was just this seems slow and it could be faster, and then how do you deduce? Like for example, are there debugging or other visualization facilities or things that would suggest that change, or is it just kind of like you have to be a smart Bayesian person and know that's the right thing?
No, that's a great question. I mean, I think the current state of Tabular is weak on that point, definitely. So that's somewhere where we could do much better. I don't think there has there's not been nearly enough research on debugging Bayesian models. So what often happens, I'm afraid, is you see these beautiful models you can tell a nice story about, but then if you stray off the happy path, if as you're learning, then you find it's difficult to get back onto it. So yeah, that is an issue. Yeah. All right, thanks for your attention. I'll see you tomorrow afternoon.